Conservative vector fields, part 2. Now we have this vector field, 2x plus 2I plus 2yj. We saw that from the previous problem. Let's see if we can find this potential function such that the negative gradient of p equals f. We can put arrows over that if you want. They're both vectors. Basically, to think of this, when we do the gradient, we take the derivative to get f. We'll take two partial derivatives to get f. And to get from f back to p, we have to do two integrations. You have to do an x integration to get this and a y integration to get that. So we're going to start with negative p of y. This should be p of xy, sorry about that. We can do an antiderivative of 2x plus 2 dx. You could start with either one of these, by the way. So you could do an antiderivative with respect to y to figure out what the potential function is. But I just arbitrarily chose x. I get x squared plus 2x plus some function of y. If we took a derivative of this to produce this, there could have been a function of y that would have disappeared. Now the question is, what is this? If we take a y partial, we should get this function right here. We're basically integrating and then differentiating to get this. So you integrate to get back to the back to p, and then you're going to differentiate to get this. So we take the y partial. These two terms drop out, of course. The y partial of that we call g prime, and you set that equal to 2y. It's a very consistent process. You integrate this, take a y partial, set it equal to that. So we get g prime is equal to 2y. G is going to be the antiderivative of that, which is y squared. You can plug that back in there. Well, guess what? That's the negative of p, so p is going to be the negative of that. And we just write p of, I don't know why I wrote p of y there, p of xy equals negative x squared plus 2x plus y squared. That's our potential function. Okay, that should work actually for figuring out line integrals. Let's test our theory out. You can actually check this if you want. If you take an x, you can get rid of the negative, take an x partial, 2x plus 2 is that. Take a y partial, we get 2y. That should be a visual check. I wrote this out here, and you can certainly inspect that. Now let's return to our previous problem. Let's suppose we want to find line integral along c of f dot dr, where c is y equals 2x, where x goes from 0 to 4. And so we're basically going from 0, 0 to 4, 8. We better get 88 for an answer. Well, let's guess what? We can evaluate this line integral as p of the initial point minus p of the final point. Plug in the initial point. We get negative 0 squared plus 2 zeros plus another 0 squared minus, this minus is that minus right here, negative 4 squared plus 2 times 4 plus 8 squared. Okay, this is all 0, that goes away. Negative, negative is positive. And guess what? We have 16 and 8 is 24, and 24 and 64 is 88, quite simply put. Okay, makes sense. Just one more thing, just to add something onto the end. Here's an interesting vector field. W of xy is equal to negative mgj. What is that? Mg is the weight. It's in a downward direction. This is a basic vector field for a weight close to the surface of the Earth. It's inescapable. Everywhere you go, it's the same thing. You can only change this by going up into outer space and going a substantial distance away from the center of the Earth. What is a potential function? Potential energy, this is what you learned about in high school physics, is mgy. And this is assuming we choose some place where potential energy is 0 at y equals 0. It's kind of arbitrary where we choose potential 0, but we won't get into that. You can actually add a constant to this if you wanted. It could be mgy plus some constant, 58. We could give everybody more potential energy for free. And I guess if politicians were physicists, maybe they would do that. Pass legislation that everybody gets a little bit more potential energy. So, and guess what happens? What's the gradient of P? It's Pxi plus Pyj. In this case, the x partial is 0, and the y partial is what? Mgj. Now, what's the negative gradient? This negative mgj. Okay, it's right here. So that agrees with basic high school physics. We're just generalizing that. In high school, you just don't talk about vector fields because you're not there yet. In high school in the U.S., it seemed like physics teachers are afraid of vectors. So whenever we pull vectors out, they run in the back room and hide for some reason. So, okay, that's all for that.